Hey everybody, welcome to acid-base reactions part 2. So today's video is going to be all about what happens when we mix weak acids and strong bases to make an equilibria system, or when we mix a weak base with a strong acid to make an equilibrium system. So let's just dive right in so we can figure out how to do all these different types of problems. So keep in mind, whenever you have a weak acid, that thing's not going to completely dissociate in solution. So if that reacts with a strong base, what you're going to make every time is a salt and water in an equilibrium system. So our first example says Colette's working in the lab and mixes 35 milliliters of 0.2 molar HClO acid with 25 milliliters of 0.25 molar KOH. What's the pH of the resulting solution? So whenever you get to one of these problems, I strongly recommend that you read it through twice. What are you actually given? What is it asking you to find? So HClO is not on our list of strong acids, which means it must be a weak acid. And KOH is on our list of strong bases. So we know this is going to be a weak acid, strong base problem. Obviously, you first know that it's going to be a weak acid, strong base problem because I'm introducing it to you this way, but this is how I want you to think through these problems when you don't have them structured this way with me. So first things first, we want to calculate the molarity of the acid and the base once mixed. And we've done these problems a million times before, so I want you to try and just pause the video real quick. After mixing, figure out what the new molarities of our acid and base are going to be, and then come on back. Okay, so I did the problem, and this is what I ended up with. So our new acid concentration and our new base concentration once mixed, you should end up with these values right here. Keep in mind that because this is a strong base, this is how it's going to break up. It'll dissociate completely into those ions. Because in our next step, why this is important is what we're going to do is create a BCA table, essentially. But I'm actually going to call them something different. Know that they just are BCA tables, and if you want to use this as a BCA table, please go ahead. It's no different. All we're looking for is the stoichiometry of our situation. What we're trying to figure out is, are we at the equivalence point of this reaction? Because if we are, it makes our lives a lot easier. If we're not, we have to do an extra step. So to figure out if we're at the equivalence point, we're essentially like just taking counts of everything that we have. Are we going to run out of one of our reactants, or are they going to react completely? So what we're going to use is called an IC table. An IC table stands for initial, change, and final. The way that I want you to think about it, and the reason why I'm using the IC language instead of the BCA language, is because if we are at the equivalence point, then our reaction, the rest of our math proceeds differently. And you'll see an example of that next. So here's how we fill it out. We start out with our initial concentrations of everything. So for our acid, we know that our initial concentration is 0.1167 molar. For our hydroxide, we know that our concentration is going to be 0.142 molar. So keep in mind, the reason why I'm writing it like this is because of this base dissociation, right? Our OH is going to be the only thing that I care about reacting. Potassium here is a spectator ion. So I just am not including it in my IC table. I'm using the net ionic equation here. So our acid is going to donate a proton to the hydroxide, which is going to form water, and that leaves us left over with the ClO minus ion. So at the beginning, are we going to have any concentration of ClO minus? No. So we're going to write a 0 in right there. Water is our liquid. So it's never going to show up in our K expression, our equilibrium constant expression, so we don't care about it. Who cares? Bye. We don't care about you. We don't need to take you into account here. Sorry, water. But you can just X this out. So now let's figure out, by comparing our initial molarities, what's going to happen. Well, our reactants are reacting in a 1-to-1 ratio. So if we don't have equal amounts of our reactants, we're going to have something left over. We're going to have a limiting reactant. Which one's going to run out first? Just the one that's smaller here, since they're in a 1-to-1 ratio. So this tells me my hydroxide is going to run out first. I'm going to use up all of my strong base, and I'll have weak acid left over in solution. So I know that I exactly am going to use up all my base because this is my limiting reactant. So my change value is going to be 0.1042, because in order to get to 0, I got to lose all of it. But the nice thing is that that's going to be my change value for everything now, right? I'm going to lose 0.1042 moles of my acid, because they're in a 1-to-1. And the exact same thing with my conjugate base now. I'm going to gain 0.1042 moles of this, because it's in a 1-to-1 ratio. So at the end, I'll end up with 0.1042 moles of my conjugate base. And how much acid will I have left over? Well, I just have to plug that into a calculator real quick, and I end up with the value of 0.0125 molar. So what does this mean for us? Why are we doing the ICF table? Because if we are not at the equivalence point, we have to proceed according to one direction of our math that I'm going to walk you through. So here we are not at the equivalence point. We do not have equal amounts of our acid and our base. So what do we actually have left over in solution? We have our acid and we have the conjugate base left over. So why is it important that OH is our limiting reactant? Because it's totally used up. Oh, excuse me. Because it's totally used up here. So that's going to make it really nice, because all we have to worry about is the acid and its conjugate base. So what we can do is, moving on to step 3, we're going to use our results from step 2 to create a rice table to figure out what we have left in solution. And you've done this before. You've used rice tables to determine pH from weak acid solutions. So hopefully this is going to feel familiar. So how much of our weak acid are we going to start with initially? 0.0125. After our reaction has happened, this is how much extra leftover stuff we've got. We never care about water in these, so I'm going to cross it off. So after our reaction has happened, we do have this weak acid left over, right? But this is still in an equilibrium system. So I'm going back and forth between this weak acid and its conjugate base in an equilibrium system as it reacts with water. So I'm not going to start out with any initial concentration of the hydronium ion, but I will start out with some concentration of my conjugate base. Specifically, I will start out with 0.1042 moles of my conjugate base, because that's exactly what I found in my IF table. So now we can solve this problem just like normal, like how we did the other ones. We're going to lose X amount of this acid and gain X amount for our hydronium ion and our conjugate base. So at the end, at equilibrium, we'll have these concentrations of all of our ions. So here we've got two things that are subtracting X out of the equation. And I know that I'm going to have to do that Ka calculation to solve for what that X value is. But what we can do is assume X is small. And we can do this. This is okay for both. For both the acid and the conjugate base. This change is going to be so small compared to the initial concentration, so we are allowed to do this. We cannot do this for the hydronium ion, though, because anything is significant compared to an initial concentration of 0. So that's really why we can subtract out X and consider it negligible for the other things. The change in concentration is super, super tiny. But compared to 0, anything is not really tiny, so you do have to account it for things that start out with concentrations of 0. So now let's solve this problem the same way we know how. Ka, our acid ionization constant, is equal to the concentrations of our products, H3O+, and ClO minus over the concentration of our reactants, HClO acid. So we were given a Ka value for this acid up above. It is 2.9 times 10 to the negative eighth. Plugging in all of my x's, I end up with 0.142, 0.1042 x in the numerator, and then the denominator 0.0125. So doing some quick algebra, plugging in the calculator, solving for x, we end up with an x value of 3.479 times 10 to the negative ninth. And why do we care about this x value? Because what we're still trying to do is calculate pH. And we know that pH is equal to the negative log. pH is equal to the negative log of our hydronium ion concentration. So here, the x value is the hydronium ion concentration. So all we have to do is take pH of that number, and we end the negative log of that number, and we end up with our pH value for the solution. So pH is equal to 8.46. All right. So this is an example of how to do one of these problems. You have one practice problem right here to complete. Go ahead and do that, check in with the answer key, and then come on back. All right, next situation. Let's say now we have a weak acid, strong base equilibria situation, but now we are at the equivalence point. So what does that actually mean? Well, it means that our concentrations or our amounts of our acid and our base are equal. This is going to make our lives a lot easier. So I'm going to walk you through this like in an exhaustive table situation. But once I show you how to do these, you can actually just go through like the quick cheat step. But let me show you what this is going to look like all thought out. So Kyle's working in the lab and mixes 50 milliliters of a 0.5 molar HClO solution with 50 milliliters of a 0.5 molar KOH solution. What's the pH of the resulting solution? And again, we're given the Ka value for HClO acid. So to start, we always have to calculate the molarity of the acid and the base once mixed. But we have equal volumes, 50 milliliters, add it together and you get 100 milliliters. And we have the same molarity, 0.5 and 0.5. So without actually writing any math down, just try to do this in your head. What is this actually going to look like? We have the same volume and we have the same molarity. So what is this going to look like if we plugged it in? Well, since our molarity is just changing by volume from 50 to 100, our volume is doubling, which means our concentration will half. So each halves. So concentration of both HClO and OH minus is going to be 0.25 molar, which is awesome. So now we do an IF table to figure out if we are at the equivalence point. If we are, we will not have a limiting reactant. If we are not, we will have a limiting reactant. So think about our initial concentrations, 0.25 and 0.25, and we'll have no initial concentration of our conjugate base, and we don't care about water. So these are equal amounts. I have equal concentrations. So what's going to happen? I have no equilibrium, or I have no limiting reactant. I'm at the equivalence point. So both of these reacting in a 1-to-1 ratio are going to run out at the exact same time. But as this reaction is happening, I am producing some of my conjugate base. So there is a final concentration of my conjugate base that I have to be aware of. But we have no extra acid, we have no extra of our strong base, which is good. All we have is conjugate base. So if we are at the equivalence point, what you can immediately do is instead of doing this ICF table, you can just say, oh, we're at the equivalence point, acid and base have neutralized each other. All we have left is conjugate base. And if you know the concentration of your acid and your strong base, you'll immediately know the concentration of your conjugate base at equilibrium because it's the same value. So what we can do now is use this to help us with step 3. So we're going to make our rice table, and what are we actually going to plug in here? Well, at equilibrium, all we have left is conjugate base and then water. So what's that system going to look like? Our conjugate base is ClO minus. This is reacting with the water. And this will form an equilibrium system to produce what? Okay, think about what's going to happen. We have a conjugate base. So this thing is acting like a base. That means water's got to be acting like an acid. What are we going to make? Well, that base is going to take an H from the water. So we're going to produce HClO minus. No, HClO, sorry, no minus. Get rid of that minus because we added in the proton. And what's left over from the H2O? Well, it lost one of its H's, so all we have left is OH minus because we took away a proton. All right. So how much of everything are we starting with? Well, our ClO minus, we know we're starting with 0.25 molar of it. Don't care about our water. And we have none of this stuff to begin with. Okay? So we're going to change by losing X amount and adding X amount to each of these because everything reacts in a 1-to-1 ratio. 0.25 minus X, we're at X, we're at X. Looky here, we're going to assume X is small. This is something that I know I write it out every time, and I don't know if I've made it very explicit, but this is something you should write every time. Every time you make an assumption, you got to tell people you're making an assumption. So you're just going to say like, assume X is small or assume X is negligible, that kind of stuff. Okay, now we go back over here. All right, so we're taking a base and reacting it with an acid, which means we don't have a Ka that we're working with here. We need to deal with a Kb, but we are not given a Kb in this problem. All we are given is a Ka, but that's not an issue. So, not given Kb, don't have a breakdown. How can we solve it? What do we know about Kb if we're given Ka? Well, what we should know is that Kw, the ionization constant of water, is equal to Ka times Kb. So if I can rearrange this formula, I get Kb is equal to Kw divided by Ka. So now I just have to plug these ones in. I know that Kw is 1.0 times 10 to the negative 14th, and I'm given the Ka for this acid as 2.9 times 10 to the negative 8th. So when I solve this out, I get Kb is equal to 3.4 times 10 to the negative 7th. Great, now I have a Kb. Problem solved. So Kb is 3.4 times 10 to the negative 7th. This is going to be equal to the concentrations of my products, which I know that solving for them in, or putting them in as x's, is going to give me x squared. In the denominator, I have 0.25 minus x, but I can assume x is small, so I'm just going to divide by 0.25. Rearranging the equation, solving for x, plugging it in my calculator, I end up with an x value of 2.915 times 10 to the negative 4th molar. And why do we care about this? What is this actually telling us? Well, in this case, our x value is equal to the concentration of our hydroxide ion. So if I want to solve for pH and I have hydroxide, I first have to solve for pOH, which is the negative log of my concentration, my hydroxide concentration. I end up with this being a value of 3.53 after plugging in my calculator. So to get pH from this, I take 14 minus my pOH, which is 3.53, and I end up with pH is equal to 10.46. Put a box around it, and you're done. All right, you got one practice problem on the next page for you to help work through. Finish that, come on back, and we'll do our last weak acid type. All right, here we go. Last one for weak acid, strong base. This is after the equivalence point. Okay, so think about what's actually been happening. We started out before the equivalence point where we have weak acid and we have strong base reacting together in a neutralization. We've used up our strong base, and then that was before our equivalence point. Okay, at the equivalence point, this tells us that our weak acid and our strong base are equal to each other, equimolar. Now we're at this point where we've added extra strong base in. We are after the equivalence point here. Okay, so Clem is working in the lab and mixes 35 mils of 0.2 molar HClO acid with 55 mils of 0.25 molar KOH base. What's the pH of the solution? Okay, so we got to first start out by finding the initial molarities. Go ahead and pause the video, find those initial molarities, and come on back. Okay, so here's what you should have found for this one, for our acid. And then for our base, here's what you should have found. Okay, so take a look at these two numbers. Are we at the equivalence point? Find out using an if table. So we're starting out with 0.0778 molar for the acid. And for our base, we're starting out with 0.1528. So these two things are not the same, which means we're going to run out of one first. Which one do we run out of first? The weak acid. This is our limiting reactant. Okay. So if this is our limiting reactant, we're going to lose this much acid from each, or this many moles for each of our reactants because they're reacting in 1-to-1 ratios. We're going to gain this for our conjugate base. We don't care about water. So here are our final concentrations, 0.075 after the reaction has occurred. All right, so at this point, we have extra strong base left over. Why is this important? Okay. So think about what's actually in our system. You have strong base and you have conjugate base. Conjugate bases are, who really cares? Not very strong, usually pretty weak. Strong base is strong base. So here's why this is important. In general, in an acidic solution, only the strongest acid will contribute to the concentration of hydronium ions. In general, in a basic solution, only the strongest base will contribute to the concentration of hydroxide ions. So why does this matter? We've got two bases here, OH and ClO minus. OH is a strong base. So what that means is our lives are so easy now because all we have to care about is the fact that our strong base is still present. So what we can do is all we have to do is use the molarity of the remaining strong base to calculate pH because it contributes to hydroxide concentration way more than any conjugate base that's in reaction. So to find pH, all we have to do is start by knowing that we're going to find POH because we have a concentration of hydroxide ions left over. And how much do we have? 0.075 molar. So negative log of 0.075. This gets us 1.12. So the pH of our solution is going to be 14 minus that answer, which is going to get us pH is equal to 12.88. So there's our final pH. So this situation, weak acid, strong base, where you're after the equivalence point, it's just all that matters is that you've got extra hydroxide in your solution. So that's really all you care about in order to calculate that final pH. Okay. last one that we're going to deal with is part 4. This is weak base and strong acid equilibria. Okay, so if you have a weak base and a strong acid, what are you going to make? You're going to make a conjugate acid and water in an equilibrium system. So our example, Aiden's working in the lab and mixes 30 mils of 0.2 molar NH2OH with 15 mils of 0.2 molar HCl. What's the pH of the resulting solution? All right, first step, as always, calculate molarities once mixed. Go ahead and do that for a second, and then come on back to see if you got the same thing I did. All right, so concentration of your base once mixed is going to end up with 0.133 molar. And concentration of your acid once mixed is going to be 0.067 molar. Okay, so we're mixing these two things together. Let's figure out if we're at the equivalence point. So 0.133 molar for our base. For our acid, we have 0.067 molar. We start out with none of our conjugate acid, and we don't care about water. So we do not have equal concentrations of this, even though they are reacting in a 1-to-1 ratio, which means one of them is going to run out first. Which one is it? It's the acid. So if this thing's going to run out first, we're going to lose exactly that much while gaining exactly that much of our conjugate acid and losing that much of our base. So after the neutralization has occurred, how much base will we have left over? 0.067 molar. So we have leftover base and conjugate base. So sorry, we have leftover base and conjugate acid. I don't know why I said that. So this means we have to account for this extra amount of this in the next step. Okay, so what species do we have left in solution after neutralization? That's the part that I just went over. Sorry, I wanted you to think about it for a second, and then I got tripped up because I said something wrong. All right, so use your step 2 results to create a rice table. So what do we have left? All right, well, we've got our base left over, NH2OH. This thing's going to react with water, and what are we going to make? We're going to make conjugate acid and hydroxide. Okay. So, how much of our base do we have? 0.067, but we also have conjugate acid left over, 0.067. We don't care about water, cross it off, and we have no hydroxide initially that we got to concern ourselves with, okay? So we're going to lose some of this, we're going to gain some of this, we're going to gain some of this. So at equilibrium, here are our final concentrations that we have to worry about. All right, so once again, we're going to assume X is small for this situation to make our math lives easier. So we're dealing with a base here, so we're going to write out a KB expression. And what are we going to have? Well, we're going to have concentration of our products. So I'm just going to write these in as their X values. So I have 0.067 from my conjugate acid, and for the hydroxide I have X. Remember, I've assumed X is small, so I'm just going to write it out like this. And then over the concentration of our reactant, and since we're assuming X is small, this is what I've got left over here. Okay, so I was given a KB value right up there. So my KB is equal to 9.1 times 10 to the negative 9th. 0.067x divided by 0.067. I love when math works out like this because now we can just cancel those two values. And we know that x is equal to 9.1 times 10 to the negative 9th molar. Why do we care? What is this representative of in our system? Concentration of hydroxide. All right, so if that's the concentration of hydroxide and I want to find pH, all I got to do is plug in POH is equal to negative log of 9.1 times 10 to the negative ninth. Plugging this in my calculator, I get a value of 8.041. And then to solve for pH, I take 14 minus that value, and I get 5.96. Put a box around it, and you're done. All right, so the last thing I want to give you before I give you like a big practice problem review is this idea of half equivalence points. So half equivalence points occur when your acid is equal to, the concentration of your acid is equal to half the concentration of your base, or half the concentration of your acid is equal to the concentration of your base. So you can kind of use this as like a cheat code. If this happens to be true, then for weak acid, strong base neutralizations, your pH is going to be equal to the pKb. For weak base, strong acid neutralizations, the pOH is going to be equal to pKb. So this is something that you can use to like check yourself at the beginning. If either one of these situations is true and you're at the half equivalence point, you can use this to like help your math go a lot faster rather than having to write out the ICT tables and the Rice tables. All right, try this last practice problem right here. Check your answer with the answer key, and then you're done.